Okay, in this video, we will see how we can apply the inputs in Mealy and Moore type FSMs in correct way. So this is not a video on the experimentations of the Mealy or Moore machine. Rather, it's just a small part of the experiment. In the lab, you will learn, or you must have already learned, how to code for Moore and Mealy type FSMs. So in this slide, you can see that this is a Moore type FSM state diagram for 1-1 overlapping sequence detection. For this, I have written the code here, and here I have stated 2 steps for properly viewing the outputs. So we will go through these steps later in this video. Then also for Mealy type, I have written the code here. And finally, for 101 overlapping Mealy type sequence, a bit complex sequence, I have given the code here and the corresponding vector reference file. So what we will do, our goal today is to see what modifications need to be done in the given input signals in order to view the output properly. Okay, so let us start. For very simple problem which you have already done in your theory part, the 1-1 overlapping Moore sequence, this is the code. So in this code, I have declared the inputs and outputs here, and I have declared 3 parameters. Let me show you side by side for your convenience. Here is the Moore type FSM, and here is the corresponding code. Okay. So we need 3 states, A, B, C, and I am assigning 0, 0 for A, 0, 1 for B, and 1, 0 for C. So you can see that what we had done in our class before in the theory part, in case of the state assigned table, this is the state assigned table. We are basically using the state assigned table, and we are converting this table to this line. Okay, we are assigning ABC to some binary values. Okay, so now let us come back to the code. Here we can see 3 always blocks. We have already learned about the always block. For sequential circuits, you will have to use this. Okay, so in this is one part, this is another always block, and this is the last always block. So what you need to understand that if you look at this picture, and if you try to recall from our theory classes also, you will understand that the next states y1, y2, the capital Y, and also the Z or output value, these are just combinational logics. Okay, only the small y, or which we call the present state, the present state is only dependent on the clock edge. That means in the output waveform, we will see that only the next state or the small y values will depend on the clock edges, and on the other hand, the capital Y and Z, they will not depend on the clock edge, they will be just the combinational logic. So here we are defining the combinational logic for capital Y here in this mode type. In sensitivity list, there is small y and w. You know how they work already, and I hope so. So if you are in state A, and if you get w equal 1, then you your next state will be B, otherwise next state is A, and this same logic will go on for other cases as well. Now in this second always block, here okay, now in this second procedural statement, okay, these three blocks are called procedural statements. Okay, inside the always block we execute the procedural statements, you know that already. Okay, now in this second always block we can see the neg age resetn and pos age clock. So it means that either if we encounter the 0 or downward edge for resetn signal, okay, and for that if we the resetn is equal to 0, then y will be initialized, or the present state will you will go back to the initial state. This is what it means. Else y, the small y will get the value of capital Y. But when? It means that this operator is the non-blocking statement, you already know that. So it means that when in the next clock cycle for one execution, okay, for one execution, suppose y has been evaluated as y equal b, and previously y was equal to capital Y was equal to a previously. So after when this execution is being done, when the next state has been found as b, but this y equal b will not be used here. Rather, the capital Y value calculated in the previous cycle. That means when in the previous cycle when we calculated y equal a, this uh, y equal a will be used in y, and in the next cycle this y equal b will be assigned inside small y. Okay, so this is how this non-blocking assignment works. You learned about it in experiment 3, I believe. Okay, so after this part, so you know that if this assignment, the capital when the capital Y is being assigned to the small y, it is not being done in the same cycle. Okay, you need to have a positive edge of the clock signal in order to perform this. So basically your capital Y will remain calculated with with certain kind of value like a, b, or c, and when you get the pause edge of the next clock cycle, that y value will be assigned inside small y. This is how it will work. So the small y will only get updated when you encounter pause edge of the clock. Okay, this part is gone. Now in this third procedural part, this is also combinational logic. It's very simple. As we have seen in Moore type, the output z only depends on the present states. Okay, so when the present state is a, z equals 0, when b, z equals 0, and when it is c, z equal 1 is stated here as well. Okay, so this is quite easy. So let me go back. I've already said that you will learn about this, or you have already learned this in the offline lab class. I will only focus on the input giving step. So okay, after compilation is done, you'll have to create a new vector form file. You can do this following the steps, this PDF. Okay, you can simply follow the steps here. First you should take the clock, then the input signals. So these three are our input signals. Okay, clock, reset n, and W. Now take the next states. Now take the present states. Finally the output. So these all of these are outputs. Okay, and the first three are inputs. You have to keep it in mind. So we will only apply values to the first three signals, and we will observe the output values appearing at these three pins, capital Y, small y, and Z. So first we give it this. You can also change its period as if you want. And reset n means if we keep reset value 0, it will reset everything. So for only the first cycle of the clock, I want to keep the reset signal 0, and for all other, for the rest of the time I want to keep it high. So first use forcing high, then okay. Now I will show you the usage of waveform editing tool here. Click this, then come back here. I want to make the value of reset and signal low for from 0 to 10 nanosecond. Okay, so I will just use the mouse, and like this I have set it to low. Now for 1-1 detection, I can give it any custom sequence to the W. I want to give like something like this. First 1-1, then 0, then 1-1-1, again 0, then 1-1-0, then at 1. Okay, so what I have applied to my input or W is 1-1-0, 1-1-1-0, 1-1-0-1. But you need to keep in your mind that first you have to apply the clock, then depending on the clock period, you will give the input to the rest of the inputs. Okay, but or to the input pins. So the reset n will remain low for one period, then it will remain high for the rest of the time, and the W values, these W values are applied for one whole clock's period. Okay, for 0 to 10 it's 1, 10 to 21, 20 to 30 0, 30 to 40 1. So what I'm trying to say is that since we are basically concerned with detecting the values at the positive edge of the clock, so you have to maintain the W value for one whole clock period so that we can get its value at the positive edge of the clock. So now if you just simulate using this setup without any kind of inversion in the clock or without any kind of offset, which I am going to give a while later, you will basically just see some kind of input as outputs that will seem confusing. So there will have to be some changes made to the signals, the input. So what I will do, you first need to invert it. Go to value and then invert. Okay, then to the reset signal and W, we will have to introduce some delay. Value offset waveform interval, I will introduce 0.5 nanosecond, or okay, 0.5 nanosecond delay here. So see, the reset signal is now shifted in the time scale a bit to the right. I will do the same for W signal as well, 0.5 nanoseconds to the right. Okay, so my all the steps required are done. I've also stated these steps in my slide. In the lab slide, you will find these steps which I have performed here. Okay. Now let us do the rest of the steps. Functional must be selected, not the timing. It's also stated in the lab sheet, or sorry, the lab manual. Then go to processing, generate functional. Okay, I have to save it. Now start simulation. Okay, so now at a glance, if you want to see whether your simulation is correct or not, the first and easiest way to check this is to see whether for 2 consecutive ones or 3 consecutive ones or so on you are getting output high or not. So here see, we applied W equal 1 for 2 cycles. So you might ask why the output is not high here. Because here we have also used the reset n signal for the first clock cycle. It is a good practice to use reset n for the first clock cycle. Okay, this is 0. That means this period or at this time range, whatever input you are getting, doesn't matter, whatever input you are giving to your W value, the code says that when reset n equals 0, Y will be initialized, which is also being done here as well. Okay, this small y, it is getting 0 value. Okay, it is getting 0 value. Okay, let's come back later to this. So what you can see that because of this particular resident value at the beginning, this 1 is not being detected here. Okay, just one value of W is considered here, and for only one, just single one, you will not get Z equal high. Then come here, see that W, though a bit shifted, the time scale W gets high here. So if you see this clock cycle, this clock is getting positive edge here, but in this time instant the value of W is 0. Okay, so basically you are not getting W equal 1 at this 30 nanosecond, but at 40 nanosecond you are getting W equal 1. At 50 nanosecond also you are getting W equal 1, and 60 nanosecond also you are getting W equal 1. So at 3 different time periods, at the positive edge of the clock, this is one period, this is another period, this is another period. So in 3 different periods we are getting 3 ones. So from the concept that you have learned in theory, for mood type the output gets high in the next clock cycle. So in this clock cycle, this clock cycle it was high, this clock cycle also it's high. So in the next clock cycle, after 2 whole clock cycles of W, we are getting high in the 3rd clock cycle, the Z. And for this W equal 1 also, we are getting Z equal 1 here as well, from 60 to 70 nanosecond. Okay, so this is how you can know that you are getting correct result. Also for single one there is no high in the output, and here I have also set the W value only for single detection 1 sets the Z value equal 1 for only one clock cycle. So now let's come to analyze what is happening inside. So we will need this diagram now. I will just show the analysis a bit for this mood type. Okay, so see, from the beginning, uh, when we are in the first clock cycle, we are applying W equal 1. So at this edge, at this particular edge, at 10 nanosecond, this is a positive edge, so we get W equal 1. So 1 1 is detected here. So when 1 1 is detected, and initially you were in state A, so after you get W equal 1, you should get to state B. The next state should be B, that is capital Y should be equal to B. So this is what is happening here. See, if I zoom a bit, zoom it. So when you are in initial state 0, if your present state is 0, if you get W equal 1, your code also says, and your state diagram also says, that you should, your Y or capital Y should be 1, which is true here. From here to here, your value is 1. Then we see further, but see, at this point reset n was 0 here. Okay, as a result, as our code said, that when reset n equals 0, the present state should be kept A or 0 0. This is what is being done here as well. For reset n, the small y is 0 here. Okay, then reset is set to high. We will not bother with this anymore. Now we will focus on this signal and this. After this detection, then okay, now here you see that this clock edge, at this clock edge, the small y must get updated now with the previous, or sorry, with the next state value. So before reaching this positive edge, the value of capital Y, that is the value of next state, was 1, or B state. So at this point, the small y, or the present state, must be B now, which is to here 1 means B. So now our present state is B. So what is this small portion? This is, you might think this is a kind of glitch, but not. This is not a glitch. This is a logical value, and this is perfectly correct. What is being done here? Let us analyze. See, W equal 1 up to this time period. Maybe this is 22 or 22 nanosecond. Okay, say you can see 20.47 nanosecond. Okay, after 20.47 nanosecond, the W value is still high. Okay, and you are in state 1, present state, small y equal 1 means B. So while in being in B state, okay, while you are in B state, if you get W equal 1, what should happen? While being in B state, if you get W equal 1, you should go to C state where the you should, your next state should be evaluated as capital Y equal 2. Okay, so here this is why the capital Y equal 2, but this is not your present state. Okay, if C was your present state, now your output would have been high, but from 20 to 30 nanosecond you can see that your small y is 1, that is your present state equal B state, so your output is not high, which is okay, which is correct. Okay, so for this small particular time range, I have explained why it is 2. After the W equal is set to 0 now, so you are in state B, W equals 0, or should be your next state? A state. So capital Y should be equal to 0 now, which is true here. See, after value 2, capital Y is taking the 0 value. Okay, so this part is done. Let us go to the detection side. If you try to analyze each and every part how I have shown you, you should get the correct answer, the logical answer for each of the time periods. Now see, in this case, in 30 nanosecond there is a positive edge, but at this time period, at this time instant, the value of W is 0. Okay, and okay, first let me see what is the value of small y after this. So at this positive edge, the value of small y is 0 because the next state value was 0 up to this time. So this 0 value is being transferred to this one through the flip-flop. So now at this time instant, after you get this blockage, now you are in state, present state is A. In state A, if you get W equals 0, your next state should also be A, which is true for this time range. Afterwards, in state A, when you are in state A, that is small y equals 0, if you get now W equal high, your next state should be B, that is capital Y should be B, which is true. Okay, from this to this is what? High. Now in this clock edge we are also detecting another W equal 1, and in this time in this clock edge at this at 40 nanosecond, now this value capital Y equal 1 is now passed to this value. The small y now is equal to 1, that means you are in now state B. At B state, if you get W equal 1, which is prevalent here, W equal 1 exists from 40 to 15 nanosecond. So in that case, where should you go? While being in B state, if you get W equal 1, you should go to C state. That means your capital Y should be equal to 2. So here you can see capital Y is 2. Okay, so whole time capital Y is 2. Capital Y is 2 from here to here. Now at this time, at this positive edge also, now this 2 y capital Y equal 2 is now transferred to small y equal 2. That means now you are in C state. So your C state begins from 50 nanosecond, and as you encounter the C state now, your output should be turned to high at this particular time. I mean at 50 nanosecond your output should also now become high, and it should remain high as long as the present state remains in state C or equal to value. I don't know if you are being able to keep up with this. In case you get lost in the lecture, please rewind the video. Okay, now, okay, now at this instant as well, this 2 is transferred here, so from here to here the small y should be 2 again, and while being in C state you can see that for some particular time the W was 1 for this time from 60 to 60.47 nanosecond. You can see the x-axis value here. Okay, from 60 to 60.42 nanosecond W was high. As a result, the 111, okay, the capital Y also was 2. Afterwards, when it became low, that means from while being in C state, this is your C state, from 60 to 70 nanosecond you are in C state, okay, because of this value 2. While being in C state, when you encounter W equals 0, your next state should be A. Okay, this is what is being done here. Here it is becoming A. Okay, and it maintains its value unless the W value changes again. Okay, now at this particular blockage, this 0 value is being transferred to small y. That means you are now A state, present state A, and state A, if you get W equals 0, next state 0, W equal, if you get W equal 1, Y becomes 1, that is Y, capital Y equal B, and this logic goes on. Okay, so I think I have explained well enough how to analyze your graph. In your exam you do not need to analyze, or you won't have time to analyze this closely, but you need to understand the overall working mechanism of the FSMs. That's why I have explained everything here. But what you need to keep in your mind that you have to invert this clock always and introduce some kind of small delay to these signals as well. Otherwise, what you will see in the output, you won't be able to make any kind of sense. Okay, so save it. And we will now proceed to Mealy type next. Okay, so I have used a bit complex problem for Mealy type demonstration, but this is basically the same procedure. So what I will do, I will apply the same thing for now 101 overlapping sequence Mealy type machine. I have given the code here, and we will see this kind of output Verilog waveform file. So this is the code. I will not explain anything here. The only difference is now that the Z values are changing depending on the present state as well as depending on the current inputs now, which was not true for move type. Okay, so this is the basic difference, which also aligns with our theory as well. In theory, I have said multiple times that the output of Mealy type depends on both the present state and current inputs, which is also being shown here. Okay, so this is the code, and as before, this is the one and only sequential block. Okay. This block is not a sequential, this block is a combinational block. Z and capital Y both are combinational logics. Well, one thing was not mentioned earlier. In the previous case, in mode type FSM, what I have shown earlier, you might be wondering whether the Z is depending on the clock edge, because you can see that the Z values are changing at the clock edges. But no, Z is not a sequential logic. Okay, the Z in mode type depends only on the value of the present state. And see the small y, the three nong row. Observe that the small y only gets changed only during the positive edge of the clock. That's why you are getting the ups and downs in the Z signal only during the positive edge of the clock. But that doesn't mean that Z is a sequential logic. Z is a combinational logic which consists of like y1, y2, small y1, small y2, small y3, and terms like this. Okay, this is just a combinational logic. So just keep it in mind. It might be asked during your Viva. Okay, so let us go back to this code. This is as before, this code I do not need to explain this, I guess. Here we are using non-blocking assignment, so that you must always remember that your capital Y will be calculated. Okay, it will be stored in capital Y. Your next state value will be stored in capital Y, and when in the next clock cycle, when you encounter another positive clock edge, at that time this y, the stored y value, will then be transferred to this small y value. Okay. Okay, now let us compile this. For saving time, I have already done the vector waveform file beforehand. So this is the vector waveform file. Okay, let me just initially forcing to low. Initially what you will see something like this. Okay, you will have to apply values to these signals. So in clock I will just give it any kind. You can also change it, like you can give it 5 nanoseconds as you wish. In reset signal, first you have to give it forcing high. Then using vector waveform tool, then now in this particular problem, we are trying to see for detection for 101 overlapping. So 1 1 0 1 0 0 1 0 1 0 1. Okay, maybe sequence is like this: 1 1 0 1 0 0 1 0 1 0 1. Okay, the sequence might be different. Your question might state a different kind of sequence. You will have to use that value then. Okay, now what I will have to do, I will have to invert it, inverted clock, then introduce offset value 0.4, let's say. Sorry, nanosecond. Then 0.4 nanosecond as well. This is the same step that I have used in case of Moore type FSM. Okay, it has been saved. Nice. Let us generate. Nice. I hope that everything is alright. Oh, what went wrong? Okay, my bad. I have done mistake here while giving the inputs. But seeing low, seeing low. So basically it takes from here to here. In previous case, 2 whole clock cycles are being counted for each W value. Okay, let us change this to 10 previous case. Okay, now 1 1 0 1 0 0 1 0 1 0 1. Forcing high. Okay, so now this should work. Okay, invert set point 4 seconds. 4 nanoseconds. Okay, now this is okay. All right, let's see if we are getting correct value or not. So for the first clock cycle, I am keeping this reset n equals 0. So basically this particular W equal 1 value will be discarded or ignored. After this 1 is counted. We are getting first clock edge, so this 1, then 0, then 1, and when we are getting this one, the output is getting high in the same clock cycle, which tells us that this is a Mealy type circuit. For this signal as well, 1 0 1, and when this one is showing at the same time instant, Z is also becoming high. Also for this 1 0 1 for overlapping detection, this is also getting high. So the output is showing correctly. Now if you want to analyze, say, for this particular time from 50 to 60 nanoseconds, see the present state small y was 2, that means 2 means this state, you were in C state. So while being in C state, if you get 0, you should go back to the initial state. That means your next state should be 0. Capital Y is 0, that's why capital Y is 0 here. Then for some time from what, from 59, sorry, for 60 to 60.27, for this short amount of time. Okay, what I'm trying to say, for this short amount of time, your see, this next state is being converted to present state at 60 nanosecond when you get a positive edge, and when you are in state A, and when you get W equals 0, the next state should be 0, which is true, shown here. So for this time range also, the capital Y value is 0. Now while being in state A, when the W is getting 1 here, now you should go to state B. Next state should be B, which is 2 here. Now at this positive edge, the next state, so present state is now B, and while being in B state, if you get high, your next state should be B, this one, which is true here as well. Now if you get 0, then you should get to C state, 1 1 0. Okay, so your next state is C, which is being evaluated in the capital Y. Now at this 80 nanosecond, you are now at C state. Your present state is C, and while being in C state, let me zoom in. It is there. Okay, while being in C state, let us analyze what is being done. What is happening here while being in C state? Now from 80 to 90 nanosecond, you are in C state, and in C state, if you get W equals 0, your next state should be 0. Capital Y is 0 here. That's why. Now while being in C state, if you get high, okay, if you get high value, you should go to B state, and output should be what, 101. So single 101 sequence has been detected. Your output should be high at this particular time. So let's see if it is being done here as well. W equal 1 while being in C state. Okay, and here also W equal 1, because your code also says so. You should always cross check with your code. When you are in C state, if you get W equal 1, your Z should become 1 and Y should become B. Okay, so this is also happening here. For this time period, capital Y is equal B and Z equal high, and the Z value drops to 0 at this time, because what is happening here, let us analyze this as well. So what we have seen in the code, Z will depend on this present state and your input. So you are in, at this time instant, 90 nanosecond, your capital Y equal 1 value is transferred to small y, which is the present state. So now from 90 to 100 nanosecond, your present state is now B. So while being in B state, if you get W equal 1, you should stay in B state. I mean, capital Y should equal to 1. Where am I? Okay, so B state, and also your output should be 0. Okay, while being in B state, if you get this, so Z equals 0 and Y equal B, which is true here as well. Okay, this time this output is 0. Now while being in B state, when the input W equals 0, you should go to what? C state, but output should be 0. So let us check here as well. You are in state B, your next state should be C. Okay, so that's why capital Y is 2 or C, and also your output is 0 here, which is also consistent with our code and as well as our state diagram. So this is how you can uh, analyze the output signals. Here these three are your outputs. Capital Y, next state is the present state and output. So you must never apply any kind of clock signals to any of these uh, signals. These are the output signals. Okay, you must not like mistakenly assign any kind of clock or forcing high low, anything at all. Do not assign anything at all. Okay, just assign values to your input signals. Okay, so this is it. Thank you. Okay, well, regarding the problem that I was facing before while showing this Mealy type problem, if you want to use this clock for 5 nanosecond periods, that's also fine, but a problem that you will encounter is that the waveform editing tool, this waveform editing tool only works for one grid, for one whole grid. Okay, so here the grid size is 10 nanosecond. As you can see, the grids, these are the grids, these dotted lines. So from 0 to 10 nanosecond one grid, 0 to 20 nanosecond another grid, and here you can also see that due to using the 5 nanosecond period, now within one grid there are 2 clock cycles. Okay, but we if we want I mean we need to make the grid size now 5 nanosecond, for 5 nanosecond. Okay, so what we can do, we can go to edit, then grid size, you can change the grid size now 5. Okay, now let me just forcing high, force low to set the values again. Now let me set the values again. Okay, now see, we can set the value from for 5 nanosecond period time scale or grid size. Now this, okay, 1 0 1 0 1, then 1 1. Okay, now I should not face any kind of problem in the output. Let's see. Okay, let's simulate it. Okay, so there is no problem at all, as we can see. So for this 101 we are getting 1, this 101 we are also getting 1, this 101 we are also getting high, and there is no 101 again. Okay, so this is how you can also change the grid size from this menu and grid size. If you want to change the clock cycle but still need to use the waveform editing tool, then you can use this, or you can also use another option, like you can let me show you this as well. value forcing 0. This is not recommended though, because this might introduce some kind of error. You can customize you can just customize the, what should I say, the grid size now, or the, what should I say, this you can easily drag and drop. Okay, now you are not bounded by the grid size of the output window. Okay, you can easily say, see, if you turn it off, this snap to grid option, then you are not bounded by the grid size. You can also, it's not been selected, you can extend it, decrease it, you can just drag and drop it up to any time value. Okay, but this is not recommended because you will face errors if you mess up a little bit. So yeah, I'm ending this video. Thank you.